Let's talk about notation. We're going to talk about nuclear physics, and to be able to do that, we have to talk about stuff we haven't talked about before. We need notation to make it happen. Here's the big one. Here's how I write the nucleus of uranium. It's uranium. Oh, and you know it's atomic number 92. And so I'm putting that here as a subscript. That's the atomic number. And you know that. 92 protons, 92 electrons, that determines its chemical state. Okay, it's determined by the number of protons in the nucleus. So this is about its chemistry. But in addition to the protons inside the nucleus, there's a bunch of neutrons. And the number of neutrons can vary. If there's 92 protons, it's uranium, end of story. But you can also have varying numbers of neutrons. And so we're going to put a number up here that tells us the isotope. This is the mass number. It's the sum of the number of protons plus the number of neutrons. And so a particular nucleus, uranium-238, it's got 92 protons. Protons plus neutrons, it's got 238 of them. That's the symbol which we're going to use for it. So if we look at these examples over here, lithium, atomic number 3, if we take lithium-11, which does exist, although fleetingly, how many neutrons does it have? How do you figure that out? Go and talk to your neighbors for 5 seconds, and then vote on this one. How many neutrons? 8. 8. It's just the difference between the two. 3 protons. This number is neutrons plus protons, and so if I take it and subtract it, I end up with 8. How about beryllium-11? How many neutrons? 7. Boron-11? 6, etc. This is stuff that you've seen before. Different isotopes of an element are chemically identical. Oxygen has two primary isotopes. It's got oxygen-16, oxygen-18. They're chemically identical. Both of them will form molecules of H2O, and they do so, and it's the same amount of energy liberated when that forms. It takes the same amount of energy to break the bonds, et cetera, because chemistry is ultimately about the electrons. But there's a difference between a water molecule made with oxygen-16 and one made with oxygen-18. And the difference is it's heavier. And that can actually have some surprising, although subtle effects. Oxygen-18 is a little bit heavier than oxygen-16, okay? So when you evaporate water from the oceans, and then it subsequently condenses, it makes rain and snow. The temperatures at which the evaporation happens, the temperature at which the condensation happens, it makes a difference what the mass of the nuclei are. And for instance, as the moisture works its way from the equators towards the pole and then rains out as rain and snow, it turns out that the heavier molecules are apt to fall faster. Why? They're heavier. And they're just more likely to form rain and snow, and they're more likely to kind of like come out of a cloud faster. So as the moisture makes its way from the equator towards the poles, it tends to become deficient in oxygen-18. And by the time you get to the pole, if you sample ice in the polar regions, it's deficient in oxygen-18. This is the oxygen-18 variation from the average percentage in the Earth. And you can see in polar ice, it's always negative. But how much deficient? It depends upon the temperature. And if it's colder, it tends to become more deficient because the processes of like raining out and snowing out go faster. And if it's relatively warmer, it tends to be less deficient. And so if you track the amount of oxygen-18 that's deposited in polar ice, it varies as a function of the Earth's average temperature. And so if you take a core, if you take an ice core in Greenland or Antarctica, and you can see an example of an ice core here, the different layers have different amounts of oxygen-18, and it tells you what the temperature of the Earth was at the time the ice core was laid down. And ice cores from Greenland, ice cores from Antarctica agree on this. And there's other ways to get this information from other ocean sediments and things like that. But it's a way of probing the past temperatures, very, very important. And if you have less oxygen-18, that means it's cooler. If you have more oxygen-18, that means it's warmer. So you can see it was getting cold, 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 real cold here. That was an ice age. All of a sudden, about 10,000 years ago, it got warmer, end of the ice age. And so you can see broad trends in this temperature data here. And that's just based on different isotopes. Not radioactive isotopes. They aren't radioactive. They're stable. But you can use them to do interesting things. Now, if you look in the periodic table, you get these numbers. Like if I look at boron, for instance, boron, atomic number 5, it's got atomic weight here, 10.8. But there is no boron 10.8. There is boron 10, and there is boron 11. Okay, boron has two different stable isotopes, atomic number 10 and atomic mass number 10 and atomic mass number 11. It's got two. But if you look in the periodic table, it says 10.8. How come? It's an average. It's an average quantity. If you take boron that you find in nature, there's some 10 and there's some 11. And you want to know how much would the sample weigh. That's going to depend upon the mix of the two isotopes that you have. So given that, if the chemical atomic mass in the periodic table is 10.81, what are the approximate fractions of the two isotopes that you have? Talk to your neighbors about that. I'll call for a vote in about 15 seconds. All right, what do we get? B. It's B. I'm going to have about 20% of boron 10, 80% of boron 11. 10.8 is closer to 11 than it is to 10. And there's examples of calculation in the textbook as to how you can work this out exactly. Okay? But it kind of makes sense. And the numbers you see in the periodic table, they're average values.